Imagine the same human body dropped onto two different worlds. Same lungs, same bones, same need for water, warmth, and a way home. On one world, Earth hangs huge in the sky, close enough that a radio call still feels like a conversation. On the other, Earth is a bright star, and every message is a delayed letter traveling at the speed of light. Both worlds can kill you without drama. Vacuum, radiation, dust, cold. Both also offer something Earth cannot easily give anymore. Room to build, resources to claim, a frontier that still has blank pages. This is a Quantum Files special, not an episode of Lunar Frontier, not fiction. Educational storytelling grounded in current engineering concepts from NASA programs and published research. Timelines are speculative. Physics is not. Tonight we ask a practical question, dressed up as a dream. If humans are going to live beyond Earth, where first? The Moon or Mars? And what exactly makes one of those choices feel almost within reach, while the other still waits on a breakthrough we have not finished inventing? Living is not planting a flag and taking a photograph. Living means a closed loop that keeps people alive for months and years, not hours. Shelter that holds pressure. Air that can be scrubbed and remade. Water that can be recycled until almost nothing is lost. Power that does not vanish when the sun leaves the sky. Food that arrives on schedule or grows on site, or both. Medical care that can handle a broken bone without waiting for an ambulance from Earth. Waste that does not poison the only air you have. Dust that does not shred seals, coat solar panels, or enter lungs. Communications that let Earth help when help still matters. And a way home, or at least a way to wait safely until the next ship arrives. Strip any one of those away, and a settlement becomes a survival stunt. Keep them all, and you begin to approach civilization. So, before we argue about romance, red sunsets, or Earthrise, we compare the environments that either help that checklist or fight it every single day. Here is the environmental comparison, held on screen so you can read it while we walk it. Gravity. The Moon sits near 1/6 of Earth gravity. Mars sits near 38%. Both are low. Mars is less wrong for bones and fluids than the Moon, but neither is Earth. Atmosphere. The Moon has essentially none. Mars has a thin carbon dioxide envelope, useful for some chemistry, useless as breathable air, and too thin to stop radiation the way Earth does. Temperature. The Moon swings from roughly plus 120 Celsius in sunlight to far below minus 100 in shadow, with no air to soften the blow. Mars is cold, often brutally cold, but its thin air and dust storms create weather instead of a pure vacuum knife. Day length. A lunar day and night each last about 14 Earth days, so power and psychology must survive long darkness. A Martian day, a sol, is about 24.5 hours, which is strangely human and therefore strangely helpful. Radiation and magnetic field. Neither world offers Earth's magnetic shield. The Moon is naked to galactic cosmic rays and solar particle events. Mars has remnants of crustal magnetism in places, but not a global umbrella. Mass overhead still matters on both. Water ice. On the Moon, the prize is concentrated in polar cold traps, shadowed craters that never see the sun. On Mars, ice appears more widely, including mid-latitudes and poles, though access, purity, and extraction still demand hard engineering. Dust. Lunar dust is sharp, clingy, and abrasive in vacuum. Martian dust can loft into planet-scale storms and carry chemistry that complicates seals, electronics, and biology, including perchlorates, in many soils. Distance from Earth. Average moon distance is about 384,000 kilometers. Mars ranges from tens of millions of kilometers to more than 200 million, depending on where the planets sit in their orbits. That last row is not scenery. It is the silent tax on every other row. Environments decide how hard living is. Distance decides how often Earth can catch you when living goes wrong. Now, zoom into the human animal inside those numbers. On the Moon, low gravity and long nights force underground or heavily shielded living if you want careers measured in years. Exercise becomes medicine, windows become rare luxuries. Outside, an EVA is a walk through a museum of knife-edged dust and radiation. On Mars, the longer day helps circadian rhythm, and the higher gravity may spare some of the worst fluid and bone losses, though we still do not have decades of human data at 0.38 G. Habitats still need mass overhead or equivalent shielding. Suits still fight dust. In situ, resource use looks different on each world. Moon ice is a polar specialty. Mars offers atmosphere to compress and process, plus broader ice prospects, which can feed oxygen, fuel, and water strategies once the machines work. None of that erases the body problem. A settlement is a hospital with a view, whether you admit it or not. If you cannot keep crews healthy, productive, and sane, the prettiest landscape is just a beautiful place to fail. So far, the scorecard is mixed. Mars looks more Earth-like in day length and gravity. The Moon looks more reachable, more inspectable, and more forgiving when something breaks. Reachability is about to become the main character. This is the major issue, and it deserves its own board. Typical chemical trajectories put the Moon about 3 days away, one way. Not casual, not safe by default, but close enough that abort options, spare parts, and crew swaps still live inside a human sense of time. Mars, on a classic HOE Mars-style transfer, is often 6 to 9 months one way, depending on the trajectory and the planetary geometry. Launch windows to Mars open roughly every 26 months, because Earth and Mars must line up. Miss the window, and you wait. Arrive and discover a critical failure, and you may be committed for years before a return opportunity makes sense. Look at the board. One-way travel. Moon, about 3 days. Mars, typically months. Launch windows. Moon, frequent enough to feel operational. Mars, a clock that ignores your schedule. Abort and return. Moon, hours to days can still matter. Mars, the mission may lock the crew into a multi-year arc. Round-trip crew commitment. Moon, measured in weeks to months for many concepts. Mars, often measured in years when you include surface stay and wait for the next efficient ride home. And the speculative column. If transit were weeks instead of months, Mars stops looking like exile and starts looking like an expedition with a pulse. That column is not today's flight plan. It is the reason people keep asking for faster ships. Because until travel time shrinks, Mars is not only farther, it is a different category of risk. The Moon lets Earth remain a neighbor. Mars, with current chemical flight, makes Earth a distant sponsor, sending delayed packages into a long silence. So, can we get there faster? Chemical rockets got us to the Moon, and can still send probes and cargo toward Mars. They are mature, understood, and limited by propellant mass and exhaust velocity. To cut months into something kinder, engineers study higher performance options, nuclear thermal propulsion, where a reactor heats propellant for higher efficiency than chemical combustion. Electric propulsion, including ion and plasma systems that sip propellant over long burns, powerful for cargo and for shaping trajectories when time and power budgets allow. Hybrid architectures, depots, refueling, staging from cislunar space so the Mars ship does not lift every kilogram out of Earth's gravity well. More speculative ideas appear in papers and concept studies, from advanced nuclear electric systems to exotic sails and breakthrough propulsion physics that are not operational hardware today. Be honest about the difference. A research concept is not a ticket. A laboratory demonstration is not a crew-rated vehicle. But also, be honest about the prize. Faster transit is not only bragging rights. It reduces radiation dose accumulated in deep space. It shrinks consumable mass. It widens abort and rescue options. It turns a years-long commitment into something closer to a campaign humans can psychologically finance. Until those systems exist at scale, Mars settlement remains possible on paper and punishing in practice. The question stays open on purpose. If we figure out how to cross the gap faster, the living comparison changes. If we do not, the Moon keeps winning the near term by being close enough to practice civilization under real space rules. Travel time is not the only remoteness tax. Communications lag is the second. Light itself needs about 1.3 seconds to reach the Moon one way. A conversation is slightly awkward, still conversational. Mars one way. Light time ranges from roughly 4 minutes to more than 20, depending on distance. Round trip, that becomes a delay where you ask a question and live a small chapter of your life before the answer arrives. That is not a glitch in the radio. That is the speed limit of the universe. So Mars operations lean hard into autonomy. Robots that can decide locally. Crews trained to handle emergencies without a real-time flight surgeon on the line. Store and forward data. Schedules built around when Earth can hear you, not when you wish they could. We can still make links better. Higher bandwidth laser communications. Relay satellites that keep a habitat connected when a planet rotates or a dust storm thickens. Better coding, better pointing, better ground networks like the Deep Space Network, expanded and modernized. Those upgrades make lag less wasteful. They do not erase lag. To truly make communications feel faster than light travel allows, you would need new physics or an illusion of speed through prediction, autonomy, and pre-agreed protocols. Again, leave it open. Engineering can shrink the pain. Physics sets the floor. Any honest Mars plan designs for delayed Earth, not for a mission control joystick that never lets go. Put the boards side by side one last time. The Moon is harsher in some environmental ways, softer in the ways that decide whether a first city can learn. It is close, inspectable, reachable on a human clock. It can become a rehearsal hall for closed-loop living, a logistics gate for deeper space, and a place where mistakes are expensive but not automatically multi-year exile. Mars is the harder prize and the more Earth-like stage in day length and surface gravity. It tempts because it looks like a second home in the imagination. With today's travel times and light lag, it demands a maturity we are still building. So where do we live first? Most engineering logic points to the Moon as the near-term classroom, and Mars as the examination that still needs better ships and better autonomy. That is not a vote against Mars. It is a sequence. Practice civilization nearby. Then spend the distance tax when the receipt is smaller. If faster travel arrives, rewrite the sequence. If faster links arrive in any practical sense, rewrite the operations manuals. Until then, the universe is not mocking the dream. It is pricing it. This was Living on Moon versus Mars, a special on the Quantum Files. Subscribe for more space engineering stories that treat physics as the plot. And tell us in the comments which world you would choose first. knowing the distance tax is real.